Hello, I'm Roger Tipton from the University of South Florida, and I'd like to welcome you to my presentation today on numerical modeling of a fused deposition modeled embedded polymer fiber in a micro-dispensed cladding for optical fiber interconnects. So I'm interested in this topic of optical fiber interconnects, primarily because back in 2012, some researchers at MIT and IBM got together and built an optical computer. And they were excited about what optics can do. And if you think of computer server farms, for example, are being built in the Arctic, in Sweden, Nordic countries, because it's cold. And computers generate so much heat from electrical signals going through copper wires. It just requires a tremendous amount of energy to cool them. They're also, optical computers have a higher bandwidth and can therefore get more information from point to point faster. And if you think of, we used to have copper wires to our house and we had dial-up internet. We got optical fiber to our homes, and now we have streaming and Netflix and YouTube, and these things were all enabled. And that's really what we're talking about, is how do we bring that same optical technology into the computer, and what will that bring? And as you can see from the pictures here, the actual optical computer chip is large, but it's relatively small. But then the interconnects, connecting all these different chips together and these different components together, are just massive. And you have to think of these fiber interconnects are much like the patch cords that you use to connect your computer to the wall for your internet, your office or your home. A tiny optical fiber inside a huge package. And so what we were interested in is, how can we have a small board and then we just 3D print some optical fibers from chip to chip and component to component. And so that's what we're going to talk about today. And so we happen to have a piece of equipment from Inscript, one of their 3DN printers. And there's an image of that printer here. And what it is an integrated additive and subtractive manufacturing tool. And so what it has is a multi-head. So for example, here we have a camera installed. Here we have another tool for micro-dispensing. We have another tool for FDM printing. We have imaging. We have laser. We have subtractive laser for laser ablation. And what makes it exciting is all these additive and subtractive tools and imaging are in the same piece of equipment. So you can fabricate a product from start to finish in the same piece of automation. And that's exactly what we did with our optical fiber interconnects. And you can see here we're micro-dispensing a cladding material. Here we're FDM printing, and really what we got from this is we were able to extrude these incredibly smooth round fibers, as you can see here in this SEM image. This is a 75 micron fiber, and on our first day we were as small as 425 nanometers of surface roughness on this fiber, and optical fiber interconnects need incredibly smooth and round surfaces to be effective as an optical fiber interconnect. And then here we have, this is the first sample we ever made, and it's, you can see it's a functioning optical interconnect. Very exciting, very exciting. And so the next step in this process was for us to take the process control, temperature, extrusion speed, the traverse speed, and how can we optimize these to make smaller, rounder, smoother fibers. And we really started with our 75 micron fibers, because that's, we just happen to have a nozzle that would make that size. And we continued to optimize the process until we were able to eventually get sub 100 down into the 70, 80 nanometer surface roughness. And you can see here on the sample, we're using optical recognition to on these SEM images to measure such small surface variation. So we're really excited. We've now, at this point, made an optical fiber that is really small and round. But of course, the goal is always to get smaller and better, and to understand why. We're scientists. We want to understand why all this works. And so that really led us to the bunch of math to try to understand what is happening in the liquefier. And this is about pressure drop inside the liquefier in the different zones, 3 different zones in our liquefier, about the forces inside, about the power required to do this, what critical pressures we have for extruding our fiber. And so as we look at this, we come across in several of these. We have most of these measurements. We don't have temperature. And so we needed temperature in several zones inside of our liquefier. And all we had were external measurements from an IR handheld tool. And here we can see we've collected the data with that IR tool. And then what we use is that as boundary conditions in our numerical simulation. And the results from our numerical simulation, we then plugged into our math. And then we also plugged it into our CFD models here to model the flow. And from this, we confirmed, yes, we are able to get smaller, smoother, rounder fibers out of our FDM printer. And why do we want to get smaller, rounder, smoother fibers? We're in the 35, we were able to print from 35 micron and larger fibers. And these are really going to be useful for multi-mode communication, multi-mode transmission of information. And single mode fibers are much smaller. They'd be sub 10 micron, and there's a lot of useful applications for that if we could get it. And if we look at our math and our simulation, we see with our 1.75 diameter filament going into our liquefier, the pressure is exponential. So it's flat and low for a long time, and we get down around 35 micron, it starts to climb, and then it just runs away as we get smaller and smaller. And we see that in our experiments. 75 is beautiful, 17 micron is an extremely rough product. And then we have runaway extrusion. We can't stop extruding because there's just so much force that has to be relieved. And so if we go through the math, we really think that a 1 millimeter filament will really bring the pressure and the forces down, and should allow us to get to our single mode, less than 10 micron fibers, round and smooth. And we haven't done that experiment yet, and that's really because our current liquefier design, the FDM tooling that we have, we do have buckling, and the math and actual experiments show that we will need to redesign our tooling to get to use a smaller filament and make smaller product. So this is something for the future. So what we've proven is we can get a round, smooth fiber out of our nozzle, and then we have to put this in something. It needs to be enclosed in a cladding material to function as an optical fiber interconnect. And so we've modeled it comes out smooth, and then if we maintain the height above what we're printing into and the correct traverse speed, then we can continue to have a smooth, round fiber, and that is the case. And then we started printing these on surfaces. So the original idea was we'd put some cladding down, we would print a fiber, and then put some more cladding. We'd have a functional optical fiber interconnect. And one of the problems, if we have a hot liquid on a surface, one of the problems you get is surface tension. In our case, we did some math and we realized, yes, we are going to have some surface tension problems. And one of the experiments we did was running the fiber through the cladding. It just happened to be the cladding was different heights when it was produced, and the experiment, we actually ran it through the cladding, and it worked. And we immediately went, well, this solves our problems with surface tension, because we're now embedded in the cladding, and it has a uniform surface tension with the surface around it, and that solves that problem. And so just because we thought it was true, we had to go and prove that it was true. And so we did some simulation work where we embedded that fiber into the cladding. You can see the cladding is the wireframe, and here is the nozzle and the material coming out of the extruder. And it was very exciting that it actually comes out and is embedded round. And so the last part of this is, okay, now we have a round fiber in the cladding. And when we were printing on the surface, we had cooling problems. Hot fiber on a cold surface surrounded by a different temperature air. You have non-homogeneous cooling, and you end up with a flat bottom again. And printing into the cladding was once again solved this problem, because we're back in the homogeneous cooling. It's a very uniform, it's encased in a material, so it has uniform cooling around all the surfaces. So we were very excited that we thought we could have a round fiber all the way through the process. And so it's always nice when the results match what you are trying to do. And here you can see on the left in the red outline, yes, we have a round fiber with a flat bottom when it's printed on the surface. If we have the fiber in cladding and we peel that cladding away, as indicated by this yellow, now we have a round fiber all the way around the part, which is excellent smooth round fiber for optical fiber interconnect communication. So to summarize, what we did is we made round optical fibers, and we improved the process to make them smooth and round and for what we needed. We wanted to make them smaller, and we've done some work in understanding that we'll have to do a redesign to be able to make smaller fibers. We understand how to do that. We also understand that it's round coming out of the extruder, and if we optimize the processing conditions and we embed the fiber into the cladding, we can continue to have a round fiber. And if we cool it homogeneously inside the cladding, that it'll continue to be round after it's cooled. And this gives us what we need to make a functional optical fiber interconnect. We're very excited about the results. And so what we'd like to do is to thank our research team. Done a wonderful job in all the help, and we'd like to thank the NREC. That's our nanofabrication group, what we've used to do SEM and other experiments. I'd also like to thank our funding sources, Path Optical Systems, the Bullring Accelerator Grant, the CADE Prize, NASA, and the NSF I-Core program, who've all provided funding for this project. And I'd like to thank everyone for taking part in our presentation. Thank you.